Welcome to Rory Academy YouTube channel 2.0. Our new and improved channel is dedicated to showing you how things are put together, from concept to prototype. Here, we break down the art of designing, assembling, and testing real engineering systems, helping you understand the science and creativity behind innovation in power electronic-centric systems and devices in our 5-minute video clips. Now, let's get on with today's video, titled, How Thousands of Tiny Cells Power an Electric Car, inside the BEV battery module. Have you ever wondered how an electric car, sleek, silent, and lightning fast, gets its power? It all starts deep inside the battery pack, where thousands of tiny cells work together like a perfectly tuned orchestra. Each one stores just a few volts, but when connected in carefully designed series and parallel networks, they create enough energy to move an entire vehicle. Today, we'll dive beneath the surface of the battery electric vehicle to explore how these small cells are arranged, cooled, and managed inside the battery module. So sit back, hit that like button, and let's explore what really powers the future of electric mobility, the battery electric vehicle battery module. Before we dive into the details of the battery module, let's start with a quick overview of the Tesla Model S, one of the most iconic electric vehicles on the planet. Now, let's take a look at the tiny cells that make up the Tesla battery module. Each of these cells is about the size of a finger, roughly 18 millimeters in diameter and 65 millimeters tall, known as the 18650 cell, or in newer models, the larger 2170 cell. So how are these tiny cells arranged? Tesla groups them into modules, which are like building blocks inside the battery pack. Each module contains hundreds of cells, connected in series and parallel configurations as discussed in the video. And then, now, we have a quick brain teaser to help you visualize the arrangement. Now let's start with a quick overview of the Tesla Model S. The Model S combines elegant design with cutting-edge technology. It features a lightweight aluminum body, an incredible battery pack that gives it a range of up to 840 kilometers. With acceleration from 0 to 60 miles per hour in just seconds, the secret behind that performance lies deep inside its battery system. Today, we'll be taking a closer look at how battery modules are arranged within the battery pack of a battery electric vehicle, BEV, one of the most critical aspects of EV design. In this video, we'll explore the Tesla Model S battery pack, known for its sophisticated layout and engineering precision. You'll see how individual battery cells are grouped into modules, how these modules are connected electrically and thermally managed, and how their arrangement impacts performance, safety, and energy density. By the end of this video, you'll have a clearer understanding of why the battery pack is often called the heart of an electric vehicle, and how careful design choices influence everything from driving range to charging efficiency. The Tesla Model S is a fully electric, four-door luxury sedan that combines stunning performance with cutting-edge technology. Depending on the variant, it offers an impressive range between 628 and 840 kilometers, powered by a 100 kilowatt-hour lithium-ion battery pack. Under the hood, the Model S delivers between 493 and 809 kilowatts of power, translating to breathtaking acceleration, from 0 to 62 miles per hour in just 2.1 to 3.2 seconds. This remarkable blend of speed, efficiency, and innovation makes the Tesla Model S not just a car, but a showcase of what's possible when advanced power electronics and battery engineering come together. The Tesla Model S, sleek, powerful, and one of the most advanced electric cars ever built. But what exactly makes this machine tick? Let's break down the three main components that define its performance: the car body, the drive unit, and the battery pack. First, the car body. Made primarily from lightweight aluminum, it's designed for both strength and aerodynamics. Every curve and contour reduces drag, improving efficiency and range. The body isn't just about looks. It's a key part of the car's energy efficiency and safety. Next, the drive unit, the heart of Tesla's performance. This unit combines the electric motor, inverter, and gearbox into a single compact system. The result? Instant torque, lightning-fast acceleration, and near-silent operation. Depending on the model, the Tesla S can go from 0 to 60 miles per hour in as little as 2.1 seconds, faster than many supercars. And finally, the battery pack, the real powerhouse. It sits low beneath the floor, giving the car a low center of gravity for better handling. Inside are thousands of lithium-ion cells working together to deliver a range of up to 840 kilometers on a single charge. Tesla's thermal management system keeps the battery at the perfect temperature, ensuring both safety and longevity. Now, let's take a closer look inside the battery pack of the Tesla Model S, where the real magic happens. Hidden beneath the floor of the car are thousands of tiny cylindrical cells, each one no bigger than your finger. At first glance, they look simple, small metal tubes about 18 millimeters wide and 65 millimeters tall, known as 18,650 cells in earlier versions of the Model S and 2,170 cells in newer models. The Tesla Model S battery pack is made up of an incredible 7,104 individual 18650 lithium-ion cells. These cells are not all connected in one massive assembly. Instead, the pack consists of 16 identical battery modules, making it easier to manage, cool, and maintain. Each module contains 444 cells, arranged in a 74 parallel and 6 series, 74P6S, configuration. This clever design allows Tesla to achieve the desired voltage, capacity, and thermal balance needed for high performance and long driving range. Through this modular approach, Tesla ensures that the battery pack delivers both power and reliability, while also simplifying manufacturing, testing, and serviceability. A true example of engineering excellence in electric vehicle design. Tesla uses 18650 Li-ion cells manufactured by Panasonic for their Model S and Model X variants of cars. The battery cells used in the Tesla Model S are called 18650 cells, and here's what that name actually means. These cells are cylindrical in shape, and each one measures about 18 millimeters in diameter and 65 millimeters in height. So the name 18650 isn't random. It's a simple code that tells you exactly those dimensions. If we split the numbers into 3 parts, the first 2 digits, 18, represent the diameter in millimeters. The next 2 digits, 65, represent the height in millimeters. And the final digit, 0, tells us that the cell is cylindrical in shape. So whenever you hear 18650, you're hearing the cell's size and shape built right into its name. 18 millimeters wide, 65 millimeters tall, and cylindrical. It's a simple naming system, but it's what helps engineers around the world quickly identify and design with these cells, the tiny powerhouses that drive the Tesla Model S. Each 18650 cell inside the Tesla Model S might look small, but it's packed with a remarkable amount of energy. Let's break down what one of these tiny cylinders can actually do. It has a nominal voltage of about 3.66 volts, a capacity of 3.4 ampere-hours, and that gives it an energy content of roughly 12.4 watt-hours. That's about the same amount of energy it takes to power a 12-watt LED bulb for 1 hour. But what really makes this cell impressive are its energy densities. It has a volumetric energy density of around 755 watt-hours per liter, meaning it stores a lot of energy in a very small space. And its gravimetric energy density is about 254 watt-hours per kilogram, so for its weight, it delivers a powerful punch. Each cell weighs just 49 grams, yet when you multiply that by the thousands of cells inside a Tesla battery pack, you get the incredible range and performance that make the Model S one of the most advanced electric cars ever built. Tiny, light, and unbelievably efficient, each 18,650 cell is a small piece of engineering brilliance that, when combined with thousands of others, powers the future of electric mobility. Now, each 18650 cell in the Tesla Model S has a nominal voltage of about 3.66 volts. That's great for a single cell, but not nearly enough to power a car. So, how do engineers increase the voltage? By connecting cells in series end to end, just like stacking batteries in a flashlight. When you connect two cells in series, their voltages add up. So, instead of 3.66 volts, you now have 7.32 volts. And if you connect a third cell, the voltage rises again. 3.66 volts times 3 equals 10.98 volts. This is the basic principle behind every battery pack. By connecting multiple cells in series, Tesla can build up the high voltage levels needed to power the motors efficiently, while still using tiny, standardized cells. So, by simply linking more cells together, we can go from a few volts to hundreds of volts, turning small battery cells into the powerful energy source that drives the Tesla Model S. Inside each 18650 cell, there's a lot more happening than meets the eye. What looks like a simple metal cylinder is actually a highly engineered electrochemical system, carefully designed to store and release energy safely and efficiently. At the heart of the cell, we have two main components, the anode and the cathode. These are the positive and negative electrodes, and they're separated by a thin microporous separator, which prevents them from touching while still allowing ions to pass through during charging and discharging. At the top, we have the positive terminal and the positive tab, which connect the cell to the rest of the battery module. The entire assembly is enclosed within a metal case, usually made of steel or aluminum, providing both mechanical strength and protection. And at the base, there's a bottom insulator, which keeps the internal components electrically isolated from the outer casing, ensuring the cell operates safely under all conditions. All of these layers, the anode, separator, and cathode, are wound tightly together in what's called a jelly roll structure, maximizing the surface area and energy storage within that small cylindrical shell. So, even though the 18,650 cell looks simple from the outside, its internal structure is a masterpiece of precision engineering, carefully designed to deliver high energy, high safety, and long-lasting performance in every Tesla battery pack. So how are these tiny cells arranged? Tesla groups them into modules, which are like building blocks inside the battery pack. Each module contains hundreds of cells, connected in series and parallel configurations. Cells in series increase the voltage. Cells in parallel increase the current and capacity. By combining these two arrangements, the battery's power, voltage, and overall range can be fine-tuned. Every module is also equipped with cooling channels, temperature sensors, and battery management electronics to keep the cells operating within safe limits. Each Tesla Model S battery module is made up of 444 individual lithium-ion cells, carefully connected to deliver both high energy and high power. These cells are arranged in what's called a 74P6S configuration. Let's break that down. The 74P means that 74 cells are connected in parallel, side by side, to form one group. When cells are connected in parallel, their voltages remain the same, but their capacities add up, allowing the battery to store more energy. So in total, you have 6 series groups, each containing 74 parallel connected cells, making up 444 cells per module. This smart combination of parallel and series connections allows Tesla to build battery modules that are not just powerful, but also efficient, safe, and perfectly balanced for the performance demands of the Model S. In a parallel connection, the voltage of the configuration remains the same as that of a single cell, but the capacity increases because the cells share the current load. Since each 18650 cell in the Tesla Model S has a nominal voltage of 3.66 volts, a 74P grouping, that is, 74 cells connected in parallel, also yields a total of 3.66 volts. Now, when we move to a series connection, things work a bit differently. Here, the positive terminal of one cell connects to the negative terminal of the next cell, and the voltages add up. So, when 6 of these 3.66 volt parallel groups are connected in series, the total voltage becomes 22 volts. In the Tesla Model S, the entire battery pack is a masterpiece of engineering, combining power, safety, and precision. Inside the battery pack, there are 16 individual modules, each built using the 74P6S configuration we discussed earlier. These 16 modules are carefully assembled together inside a strong aluminum battery tray. Each module is connected in parallel to a central bus bar through M8-bolt terminals located on the module ends. This bus bar acts like the main power highway, collecting electric current from all 16 modules and channeling it efficiently through the system. The collected current then flows to a high-voltage contactor, which controls the power delivery to the electric drive unit. Altogether, the Tesla Model S battery pack generates a total of about 22 volts per module, combining to produce an overall system energy of around 84 kilowatt-hours, enough to power the car for hundreds of miles on a single charge. So, while it looks like one solid block of energy, the Tesla battery pack is actually a sophisticated network of precisely connected modules, all working together to deliver the incredible performance, range, and efficiency that Tesla is known for. Here, you can see the top view of the module, along with a schematic illustration that highlights how all these components fit together inside the aluminum housing. In addition to the thousands of battery cells assembled inside, each Tesla battery module also contains a range of critical supporting components, all working together to ensure safety, performance, and reliability. These include the cooling system. Now, one of the most fascinating parts of Tesla's battery design lies in its cooling system. The pipes carrying the water glycol coolant solution inside the module feature a patented wavy design, a clever engineering solution developed by Tesla. This wavy structure isn't just for looks. It serves two critical purposes. First, it increases the surface area of the pipe, allowing for better heat transfer between the coolant and the battery cells. Second, it improves packaging efficiency, enabling Tesla to fit more cells within the same space while keeping them evenly cooled. The result is a highly efficient thermal management system that maintains the ideal temperature for every cell, maximizing battery life, safety, and performance. The image you see here is taken directly from Tesla's patent document, showcasing the ingenious wavy coolant pipe design that keeps the battery pack running cool and consistent, even under extreme driving conditions. The cooling pipe itself is wrapped in a thermally conductive yet electrically insulative material. This clever combination allows heat to transfer efficiently from the cells to the coolant, while at the same time preventing any electrical contact between the metal pipe and the battery cells. At the bends of the cooling pipe, you'll notice a distinct orange-colored tape. This is Kapton tape, a special high-temperature insulating material used to enhance the electrical insulation in areas where the pipe changes direction or comes close to other components. The coolant flowing through these pipes is a mixture of water and glycol, the same type of solution used in many high-performance cooling systems. It's responsible for absorbing heat from the cells and carrying it away to maintain a stable temperature throughout the module. As the coolant moves through the battery pack, it gradually picks up heat from the cells, its temperature rising as it flows from one end of the module to the other. This temperature gradient, often shown in Tesla's thermal diagrams, perfectly illustrates how the cooling loop keeps every part of the battery operating safely and efficiently. An exploded view of the cell assembly inside the battery module clearly reveals that inside the battery module, the 18,650 Li-ion cells are held vertically, sandwiched between a pair of complementary cell inserts. The cell inserts are made of flame-retardant polycarbonate plastic and contain a multitude of complementary cylindrical retaining holes called cell wells. The cell wells in the cell inserts are through holes to keep the cell terminals exposed for making connections. On top of the cell inserts on each side of the module, current collector plates are placed. These current collector plates are made of copper and contain holes that align with the holes in the cell inserts, which ensures that the cell terminals remain exposed for making connections. Each cell terminal in the Tesla battery module is connected to the current collector plate using thin aluminum fuse wires. These fuse wires act as both electrical connections and safety devices. They allow current to flow from each cell into the module's power circuit, but if a cell ever overheats or short-circuits, the fuse wire will instantly melt and disconnect that cell from the rest of the pack. These individual cell-level connections ensure that in the case of a short-circuit event, the failure is isolated and the risk of sustained arcing and a thermal run is minimized. After the cells have been sandwiched between the top and bottom cell inserts, An adhesive such as Loctite is dispensed in the space between the cell ends and the cell insert. The adhesive is expected to penetrate the interstices and spaces between the cell and the cell insert. This adhesive securely bonds each cell to the cell insert. Let's have our brain teaser to show how well we have understood how thousands of tiny cells power an electric car inside the battery electric vehicle BEV battery module so far. Alright, brain teaser time. Let's see how well you've been paying attention. Question 1. If one Tesla Model S battery module contains 444 cells, and the full battery pack uses 16 such modules, how many individual 18,650 cells are in the entire pack? I hope you have been able to figure out the right answer. Let's go to the solution. 444 cells per module multiplied by 16 modules equals 7,104 cells in the full pack. Question 2. If each 18,650 cell stores about 12.4 watt-hours, how much total energy, in kilowatt-hour, do all 7,104 cells store together? Again, quick mental math or use your phone. Answer time. Multiply 7,104 cells by 12.4 watts-hours per cell equals 88,089.6 watts-hours, which is about 88.09 kilowatt-hours of total stored energy. A quick note, you might sometimes see Tesla quoted as an 84 kilowatt-hour pack. That's because manufacturers often report usable capacity, what's available for driving, which can be slightly less than the total or nominal capacity we just calculated. So 88.09 kilowatt-hours is the rough total energy inside the cells. The usable figure can be lower after safety margins, battery management reserves, and rounding. Bonus question. What happens if one of the thin aluminum fuse wires connecting a cell to the collector plate melts? Think, does the whole pack fail? Drop the answer in the comment section. Thank you so much for watching and learning with us today, exploring how thousands of tiny cells power an electric car. Inside the battery electric vehicle, BEV, battery module. At Roar Academy YouTube channel 2.0, we help you watch, learn, and understand how to prototype real-world power electronics and energy systems. If you found this video insightful, don't forget to like, subscribe, turn on notifications, comment, and share, so you never miss our next deep dive into the world of technology and innovation.